everyone, I am Tanya Shreedhar. I am a PhD student at IIIT Delhi, India. Today, I will be discussing our work titled From Single Lane to Highways, Analyzing the Adoption of Multipath TCP in the Internet. This work is done in collaboration with Technical University of Munich and Max Planck Institute for Informatics, Germany. Multipath TCP is an extension of TCP that enables applications to transparently use all multiple interfaces simultaneously within a single connection. The protocol was proposed in 2013 and has recently been standardized in March 2020. By using MPTCP, applications can achieve significantly higher aggregated throughputs, improve resilience to packet losses, and support seamless mobility across network interfaces. MPTCP is currently being used in data center environments and has public support from large organizations such as Apple and Korea Telecom. Since March 2020, MPTCP version 1 is available and enabled by default in Linux kernel version 5.6 and upwards. However, despite such huge support, there is no recent wide-scale study analyzing MPTCP support and usage in the Internet. Additionally, understanding the adoption of multipath TCP is important primarily because of two reasons. Firstly, being end-to-end in nature, multipath TCP can only be used widely if both client and servers over the Internet simultaneously support the protocol. Secondly, MPTCP by design relies on TCP header extensions for its operations. Previous research has shown that such header extensions can be easily blocked or modified by middle boxes prevalent in the Internet, such as performance-enhancing proxies, gateways, and load balancers. The plot here is borrowed from a work published in 2012 and shows that organizations of all sizes have tens of thousands of middle boxes in their network, which can pose as a threat to operation of MPTCP. In this work, we present a well-rounded study that analyzes the support, operation, and adoption of multipath TCP in the Internet. To identify support for multipath TCP in the Internet, we actively scan for MPTCP options over the IPv4 and IPv6 address space. Our study probes the entire IPv4 address space over port 80, which is close to 74 million unique responsive IPs, and port 443, which is close to 52 million unique responsive IPs. In IPv6, we use the IPv6 hit list to probe both port 80 and port 443 due to the size of the address space. Additionally, we use tracebox to accurately identify presence of middle boxes on the path to MPTCP host and showcase how they impact the accuracies of study scanning for MPTCP support. Secondly, we identify the impact of middle boxes on MPTCP data transfers in the Internet. We investigate if the network treats MPTCP traffic any differently to regular TCP traffic. Specifically, we focus our attention on the middle boxes that do not interact nicely with TCP header extensions. Finally, we analyze the usage of MPTCP for data transfers over the Internet by investigating almost 7 years of inter-domain traffic collected by CADA and MAVI traffic monitors. In the interest of time, we only provide an overview of the MPTCP support and traffic usage over the Internet. We request the listeners to please read our paper for detailed analysis. Let's start with measuring the number of hosts that support MPTCP in IPv4 and IPv6. It is first important to understand the MPTCP connection establishment procedure before we discuss our scanning methodology. MPTCP connection establishment leverages the traditional TCP's three-way handshake. The client, in this case Bob, sends a SYN packet to the server, that is Alice, who replies back with a SYN-ACK. The connection is established if Bob finally replies with an ACK as the third packet. However, MPTCP adds a few header options to TCP Handshake for its operation. Firstly, every packet includes an MP-capable flag which denotes if the host supports MPTCP. The connection can only be established if both client and servers send MP-capable flags. Secondly, every host sends a 64-bit randomly generated sequence as its MPTCP sender's key. The sender's key is unique and is used to authenticate the host when adding or removing subflows in later stages. Keep in mind that the handshake procedure differs slightly in MPTCP version 1, which is why we only analyze support for MPTCP version 0 in this work. We use ZMAP to enumerate IPv4 and IPv6 address spaces. To identify MPTCP host, we leverage the initial handshake mechanism discussed in previous slides, that is, sending a SYN with the MP-capable flag along with the static sender's key. A legitimate MPTCP host will reply back to an MP SYN with a SYNAC containing MP-capable flag and its own sender's key. If the SYNAC response includes MPTCP header options, we classify the host as potentially MPTCP capable. These tables show a month-wise summary of our scanning results over IPv4 and IPv6 address space using ZMAP. At first glance, it might seem that MPTCP is extensively supported in IPv6 with almost 200,000 hosts consistently responding with MPTCP options. In IPv6, we find the support to be much smaller with only a few dozen hosts reportedly replying with MP-capable options on port 80 and 443. But do all these hosts truly support MPTCP in reality? Or do results from ZMAPs have possible artifacts due to middle boxes prevalent in the internet? Let's understand how different middle boxes can interact with packets containing MPTCP headers. First category of middle boxes can drop packets containing TCP header extensions altogether. Some middle boxes can strip the packet of extended headers containing MPTCP options before relaying it to the destination. In the response, the middle box can mirror the original options back to the sender. Some middle boxes can also modify the header extension in response and update the values of the sender's key with their own. Finally, the MPTCP supporting middle boxes allow the MPTCP extensions to pass through it as is. To examine if our scans are affected by interfering middle boxes, we analyze the MPTCP sender's key we receive from targets in their SYNAC response. The plots above show the Hamming weight of the received sender keys from hosts that reportedly support MPTCP using ZMAP. Since the key value is a random sequence, the ideal distribution should follow the normal distribution according to the center limit theorem as indicated by the orange curve. We find that a very large percentage of received sender keys do not follow the normal distribution. In fact, the Hamming weight of 16, that is the exact Hamming weight of the scanner's key, is heavily overrepresented, indicating meddling by middle boxes that mirror MPTCP options in our ZMAP scans. While such middle boxes can be identified by simply checking if the returned sender key matches the scanner's sender key in the SYN, however, this approach does not identify middle boxes that can also modify the MPTCP header options. To accurately analyze the support for MPTCP, we utilize TraceBox to identify the presence of middle boxes in our ZMAP scans. TraceBox allows us to detect which on-path hop modified TCP options between the end hosts. We ran TraceBox toward all potential MPTCP capable hosts and found three broad categories of responses. In the first category, only the target host modified the MPTCP options by adding its own sender key in the response. We classify this category as hosts that truly support MPTCP. In second category, an intermediate hop was found to modify the MPTCP option, either by removing or changing it. We classify these as middle box affected flows. The final category includes hosts that did not respond to our tracebox queries and were hence marked as unresponsive. The plot shows the true MPTCP support for HTTP and HTTPS in IPv4 over our study period. The blue bars are the hosts that truly support MPTCP and the green are the hosts that are affected by middle boxes that actively modify MPTCP options. We find that MPTCP support is increasing consistently in IPv4, reaching almost 5,500 hosts supporting HTTP and 4,500 supporting HTTPS. Interestingly, we found only 6 instances where truly MPTCP capable hosts were affected by middle boxes that blocked and modify MPTCP options on path. For IPv6, the support for MPTCP is much lower, with almost 30 hosts supporting the protocol on both port 80 and 443. Unlike IPv4, we found that IPv6 is completely free of middle boxes that modify MPTCP options at the moment. Let us now analyze if the growing support for MPTCP has also resulted in growth of multipath TCP traffic in the internet. To analyze the real-world MPTCP traffic share, we look at anonymized passive data traces from CADA and MAVI traffic monitors. In CADA dataset, we analyzed 4 years of traffic from 2015 to 2019 on Tier 1 ISP backbone link in North America. Using MAVI traces, we analyzed 7 years of traffic from 2014 to 2020 captured at the uplink of a Japanese university to ISP. The figures show the traffic share of MPTCP flow and bytes compared to TCP for CADA and MAVI datasets. We observe that the MPTCP share remains consistently low in the CADA dataset till 2018. From 2018, we observe a clear increase in MPTCP flow and byte share. For the MAVI dataset, we observe that MPTCP byte share remains relatively constant over time until the end of 2019. Around this time, we see a significant increase in the byte share. We also look at the flow distribution over time and find that MPTCP is starting to be used and carries actual data. We also looked at the applications used in MPTCP traffic and saw a mix of HTTPS, HTTP, Siri, RDP, Spam Trap, Microsoft services, and others. However, HTTPS traffic eclipses all other applications with approximately 99% traffic share for both CADA and MAVI datasets. This brings us to the end of our presentation. To summarize, in this paper, we present the first well-rounded assessment of multipath TCP adoption in the Internet. We uncover hosts that truly support MPTCP over port 80 and port 443 in IPv4 and IPv6 and found a rising trend. We identify middle boxes that inhibit the usage of MPTCP by modifying and blocking packets with TCP header extensions. We found that such middle boxes not only affect the accuracies of the studies analyzing MPTCP support, but also aggressively delay MPTCP data traffic. We also analyze if MPTCP data is treated any differently to the TCP in the Internet and found no difference in connection latency between the two protocols towards hosts that truly support MPTCP. We also analyze MPTCP traffic share compared to other transport protocols in CADA and MAVI traffic monitors. We find that MPTCP traffic usage has increased since 2018 and HTTPS is the most popular application that utilizes the protocol for enhanced performance. Finally, we provide a public web service at mptcp.io where you can view the continued support of MPTCP in IPv4 and IPv6 and can download our datasets and results for reproducibility and further research. Thank you all for listening. We highly encourage you to read our paper and visit mptcp.io. If you have any questions, please feel free to email us at info@mptcp.io. Thank you.